In this video we talk about series. What do we mean by a series? In the previous video we talked about sequences. This is called sequence. It's sequence a sub n from n equals 1 to infinity. This is called infinite sequence because we have infinite number of terms. If we want to write it by listing the elements, we got this representation a1, a2, a3, etc. This is called sequence. Now if we are interested in finding sum or writing this as sum of elements or sum of terms, then we call this series or infinite series. So as you can see here, we have addition or sum instead of having commas between terms. Now this is the series. Sometimes we prefer to write it in more compact form, so the notation that we're going to use is the sum. This is sigma, denotes the sum. That means we have the operation is the sum here. So the sum from n equals 1 to infinity a sub n. What does that mean? That means we substitute first 1 here to get a1, and then we add because we have sigma. Then we substitute 2 here, so we get a2. Then we add because we have sigma, and so on. So this is the notation that we are gonna use here. The sum from n from 1 to infinity a sub n. Or some people prefer just to write it as a sum without writing the limits of this sum. Now in some proofs and applications, we may prefer to find partial sums. What do we mean by partial sum? The first partial sum is the first element. The second partial sum is the sum of the first two elements. So a1 plus a2. The third sum, S3, is a1 plus a2 plus a3. So S sub n, the nth partial sum, is a1 plus a2 up to a sub n. And we can write this as the sum of a sub n from 1, or let me use different index here. We can write it as the sum of a sub I from 1 to n. We have n terms. Now if a sequence of partial sums S sub n is convergent and the limit as n goes to infinity gives some number, real number, this means the limit does exist and the series a sub n from 1 to infinity is convergent. And we write sum of a sub n from 1 to infinity equals little s. Now if the sequence of these partial sums is divergent, then the series associated with this sum is divergent. Now we have a notation here, or how to write the sum from 1 to infinity a sub n using the limits, we can write this as limit n goes to infinity I from 1 to n a sub I. Here we wrote the series as a finite series, but with limit n goes to infinity. So n goes to infinity, and here we have n. So those are equivalent series or expressions. So this says the sum of the series is the limit of the sequence of partial sums. Now let's take an example. If the nth sum of the first n terms of the series a sub n, n from 1 to infinity, is s sub n equals 2n over 3n plus 5. We want to find the sum, we want to find the sum of these terms of the sequence a sub n, or we want to find the sum of this series. In order to do that, we take limit of s sub n, n goes to infinity, because here we mentioned that we need to find limit Sn. If we find limit Sn of the nth partial sum, and that limit does exist, and the sequence is convergent, then the series is convergent. Now limit Sn is limit 2n over 3n plus 5, n goes to infinity. And since the direct substitution gives us infinity over infinity, and that's one of the L'Hopital forms, we just find the derivative of the numerator and the derivative of the denominator separately, and that will give us the limit, the sum of this series. This means the series a sub n, n from 1 to infinity, is convergent. Now we have a special type of series, and this is very important one. It's called geometric series. For geometric series, the ratio or each term is obtained from the preceding one by multiplying it by the common ratio, by some number. For example, if we have the series 2, 4, 8, 16, etc., if we divide each term by the preceding one, for example, 4 by 2, this gives us 2, and 8 by 4, 2, 16 by 8 is 2. We have constant ratio. This is constant ratio is equal to 2. This is denoted as r, little r. So if this is the same for all, I mean, if we divide any term by the preceding one, we get a geometric series. I should write addition here between elements or terms. Now we can write this in general. We can write this series as a plus ar squared plus ar cubed plus arn minus 1 to infinity, where a is the first term the first term, and then we multiply it by r to get the second term. Then we multiply the second term by r to get the third term. Then we multiply the third term by r to get the fourth term, and so on. So we obtain each term from the preceding one by multiplying it by the common ratio r. Now, after writing this in the general form, we can write it in more compact form using the series. So it's n from 1 to infinity, ar to n minus 1, where a is not equal to 0. This is called geometric series. Now, for r equals 1, we have a plus a plus a plus a if we are interested in finding the nth sum, an n partial sum. So those are n terms. If we are interested in finding the sum of the first n terms, this is Sn. This is equal to n times a, and that means this sum goes to infinity as n goes to infinity. So that means limit of Sn, the partial sum, as n goes to infinity, does not exist. Now, for r different from 1, we can derive a sum of n terms of the geometric series. So Sn is a plus ar squared plus ar cubed up to ar n minus 1. Now, if we multiply this by r, let's multiply it by r, we get ar squared, ar cubed up to arn. Now, if we subtract 2 from 1, we get Sn minus rsn equals, now we cancel these terms, and we are left with the first term here minus, because we want to subtracting rsn from Sn, we get minus arn. Now let's take Sn as a common factor from the left hand side and a from the right hand side, and then divide by 1 minus r both sides. So we obtain S sub n equals a times 1 minus r to the nth over 1 minus r. Now this gives us the sum, the nth sum of the sequence, the nth partial sum of the sequence if r is not equal to 1, and this is finite sum. Finite sum. Now, for r between -1 and 1, for example, r equals 1/2, we find that r raised to power n goes to 0, because, for example, 1/2 to the power n, this goes to 0, because when n equals 1, we get 1/2. When n equals 2, we get 1/4. When n equals 3, 1/8, and so on. So we approach 0 as n goes to infinity. So if r is between -1 and 1 and not equal to -1 or 1, then r to the power n goes to 0 as n goes to infinity. So the limit Sn as n goes to infinity, if we take infinitely many terms, then we take limit of Sn. Sn, we obtain it here, a times 1 minus r to the nth over 1 minus r, n goes to infinity. Now this term becomes 0 because r is between -1 and 1. So we get a over 1 minus r. Now this gives us the sum of the infinite geometric series. So if absolute value of r is less than 1, that means this is equivalent to this form. That means r is between -1 and 1. Those are equivalent. So instead of writing r between -1 and 1, we can write absolute value of r is less than 1. So if this is true, then the geometric series is convergent, and its sum is given by a over 1 minus r. Now a denotes the first term and r is the common ratio. So we need to remember this formula for the infinite series, sum of infinite geometric series, and this formula for the sum of finite geometric series. Now let's take an example. If we want to find the sum of the geometric series 5 minus 10 over 3 plus 20 over 9 minus 40 over 27, infinite series. If we look at this series, we can check if this is geometric series. It's given that it's geometric, but to find the common ratio r, we need to divide each one element. Let me rewrite this as this is -10 over 3. So let's divide this term, the second term, by the first term to obtain r. -10 over 3 over 5 over 1, and that's -10 over 15. Simplify, you get -2/3. So this is the common ratio r. Now if we take the absolute value of r, this is absolute value of -2/3. This is 2/3, less than 1. If it's less than 1, then the geometric series is convergent. So the geometric series, the above geometric series, is convergent. If we want to find the sum, this is infinite series, so we use a over 1 minus r. A is the first term. A is 5. Over 1 minus r, r is 2/3. -2/3, sorry. R is -2/3. This is r. Negative is positive, so this is 5 over 5/3. Now flip the denominator, you get 15 over 5, and that's equal to 3. So the sum is 3. Let's take another example. Is the series n1 to infinity, infinite series, 2 to 2n, 3 to 1 minus n, convergent or divergent? Now to determine this, we can find, now this is geometric series, because if we divide, let's find some terms of this. When n equals 1, we get 2 squared is 4 times 3 to, you write it here as, and then we simplify. So 2 to the power 2 times 1 times 3 to 1 minus 1, and this is 4 times 1, because 3 to the power 0 is 1. Any number raised to power 0 is equal to 1 except 0 itself. So the first term is 4 plus. Now when n equals 2, we have 2 to the power 2 times 2, 3 times 3 to the power 1 minus 2. And this is, now 2 times 2 is 4, 2 to the power 4 is 16. Now 16 times 3 to negative 1, 16 times 3 to the power negative 1 is 16 over 3. We can bring this down, becomes the power, the exponent becomes positive. When n equals 3, we have 2 to the power 2 times 3 to 1 minus 3. 2 times 3 is 6, 2 to the power 6 is 64, times 3 to power negative 2, and then we can bring this down here. This becomes 64 over 9, and so on. So we expanded the series here. We need to find r, the ratio. R is, we divide the second term by the first term. So this is 16 over 12. This gives 4/3. So the absolute value of r is 4/3. It's greater than 1, so it's divergent. If it's less than 1, then it's convergent. Let's take another example or application. We want to show that 0.9 infinite repeated 9 equals 1, exactly equal to 1, not approximation. This is one of the nice applications of the geometric series. Now 0.9, and we have bar over the 9, that means it's infinite and repeated. So we can write it as 0.99999 infinite and repeated. We want to show that this number, this fraction, this decimal is equal to 1, exactly equal to 1, not just approximation. We want to show this using the concept of geometric series. So we can rewrite this as this geometric series. So let's start with the first decimal place. So 0.9 plus the second one is 0.09 plus the third one 0.009 plus the fourth one 0.0009, and so on. So if we find the sum of these values, or if we add them together, we get this expression, this number, 0.9999 infinite and repeated. So this is geometric series. We find r, 0.09 over 0.9. We just divide the second term by the first term, and this gives us 9 over 100 over 9 over 10. Now flip the denominator, we get 90 over 900, and then we cancel 0, we get 9 over 90. Simplify, you get 1/10. So r is 0.1, or just 1/10. Now we find the sum. The sum is a over 1 minus r. A is the first term, it's 0.9, over 1 minus r, r is 0.1. So we can write it as fractions. 9 over 10 over 1 minus 1 over 10. Try to get a common denominator for this denominator. You get 9 over 10, and this is equal to 1. So we proved that 0.999 repeated, infinite repeated, is equal to 1. Now we have another well-known series that's called telescoping series. So we want to show that the series n from 1 to infinity, 1 over n times n plus 1, is convergent. And then find the sum, its sum. So if we look at this geometric series, we can, this telescoping series, this is called telescoping series. We can rewrite this in an equivalent form. We can find the Sn, the nth partial sum from I1 to n, 1 over I minus 1 over I plus 1. Those are equivalent. This is equivalent to this. Why? Because we can apply partial fraction technique, partial fractions. So we can write this as, we want to split the denominator into over two fractions. So a over n plus b over n plus 1. Now we need to find a and b. So we try to get common denominator here. So 1, the numerator of the left-hand side fraction, is equal to a times n plus 1 plus b times n. A equals an. Now we just distribute this. Now we compare or equate like terms, or terms that represent similar. We compare similar terms. So we have term with n here, but on the left hand side we don't have that term. So 0 is equal to a, the coefficient of n here, plus b, the coefficient of n here. So this is one equation. And the second one, we compare the constants. The constant on the left hand side is a, the constant on the right hand side is, the constant on the left hand side is 1, and on the right hand side is a. So a is 1. So we substitute it here to get 0 equals 1 plus b, and that means b equals -1. So we can write this as 1 over n times n plus 1 is equivalent to a over n plus b over n plus 1, but a is 1. A is 1 and b is -1. So plus minus minus, so we just substitute it here using I instead of n. So those are equivalent. Now we find partial sum, nth partial sum of the series. And if we expand this, let me rewrite it here. We obtain the nth partial sum from I equals 1 to n, 1 over I minus 1 over I plus 1. Let's expand this. We get 1 minus 1/2 plus, substitute I equals 2, you get 1/2 minus 1/3. Substitute I equals 3, you get 1/3 minus 1/4, plus continue in this expansion up to 1 over n when you substitute the last term, and the last term is obtained by substituting I equals n, so we obtain 1 over n minus 1 over n plus 1. Now if we cancel these terms, -1/2 plus 1/2, -1/3 plus 1/3, -1/4 plus 1/4, and so on. So we find that what is left here is the first term and the last term. So the sum Sn is 1 minus 1 over n plus 1. Now we take limit of this partial sum, limit of 1 minus 1 over n plus 1, n goes to infinity. This gives us 1 minus 0, because here when we substitute n equals infinity, 1 over infinity is 0. So we are left with 1, so the partial sum is 1. That means the original series n from 1 to infinity, the infinite series 1 over n times n plus 1 is equal to 1. That's the sum of this series. This is called telescoping series. And another important series is the harmonic series. This series is given by the series from n from 1 to infinity of 1 over n. This is divergent series. Why? Because you can substitute values here, and there's some proof for this. 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, etc. This is divergent series. Now we have some result here. Theorem: if the series a sub n is convergent, then the limit of a sub n goes to infinity is equal to 0. If the series is convergent, then the limit of a sub n is equal to 0. Now we have a test for divergence. If the limit of a sub n goes to infinity does not exist, or the limit as n goes to infinity of a sub n is not equal to 0, then the series a sub n from 1 to infinity is divergent. So if the limit does not exist, or the limit is not equal to 0, then we say that the series is divergent. Let's take an example. We want to show that the series n from 1 to infinity, n squared over 5n squared plus 4 diverges. Now to show that this is divergent series, we just take the limit of a sub n. This is a sub n. Limit a sub n goes to infinity, and we want to see if this limit does not exist, or the limit is not equal to 0. That means it's divergent. So limit a sub n squared over 5n squared plus 4, and we know that this is equal to 1/5, or we can applying the L'Hopital's rule. We find derivative of the numerator and denominator. Derivative of the numerator 2n, derivative of the denominator is 10n, and then we still have infinity over infinity, so we apply it again, apply the L'Hopital rule. We differentiate the numerator, we get 2, differentiate the denominator, we get 10, so it's 1/5. So this is not equal to 0. That means the series n squared over 5n squared plus 4, n from 1 to infinity, is divergent. In general, if limit of a sub n goes to infinity not equal to 0, then the series is divergent.